from this chapter 8, and then we'll move on to chapter 9. We've already done this one, I understand, and this one, right? Pretty sure we have. Okay, so have we done this one? We have?
Yeah.
And this one? Have we done this one? No, okay. So let's try this. I want you to rank the moments of inertia for this collection of bars. You have two identical bars, same mass, same length, and they're made into a T like this. And I want you to rank their moments of inertia. Now remember, moments of inertia is dependent upon the mass and the radius squared, or the distance to the axis of rotation squared. Yeah, that I is mr squared. So let's rank the moments of inertia from biggest to smallest. So as with all multiple choice questions, you want to eliminate answers, and that's a good attack on this type of question. And so to eliminate a good fraction of the answers, you ask yourself, which of these has the biggest moment of inertia? The one with the biggest moment of inertia has the most mass out at the biggest radius. Which one of those is this? Has the most mass at the biggest radius? Is which one? Is A, right. A has all this mass, this entire bar is out at the full radius, and none of these others have that, right? So A is definitely the biggest, so I can get rid of A and B, options A and B. And then you can ask yourself, which has the smallest? Are there any that have identical moments of inertia? And then that'll allow you to eliminate further answers. Give me about 15 more seconds. Let's stop at 210. 210. $210. All right, I think B is right. Let's see. So as we said, I can get rid of A and B because the moment of inertia for configuration A is definitely the biggest. I'm going to get rid of this. And I also know that the moments of inertia for A and B are not equal. Like these just aren't the same configuration. In fact, on this one, I have an axis of rotation here that is all along a bar. So this bar contributes nothing to the moment of inertia, right? Because the radius of this bar, or the distance to this bar, is 0. So it contributes nothing to the moment of inertia. So I can also get rid of C right here. So now I'm really just looking at D and E. And the difference in these is what they say about configurations D and D. So option D says that the moment of inertia of D is bigger than the moment of inertia of B. Is that true? It is true, in fact, because notice here, I have this bar at half the radius, and this bar extends out to a big radius. But over here, this bar doesn't contribute anything to the moment of inertia, because the radius is 0 for this bar, whereas this one contributes some, but it contributes the same as what I have here. So these two are identical. If I get rid of this bar, these two would be identical, and then I add in this extra bar, which adds on to the moment of inertia. So A is the biggest, D is the next biggest, B is the next biggest, and then C is the smallest of all. Notice how this is configured, that I have the axis of rotation down one of these bars, so this bar doesn't contribute anything at all to the moment of inertia, and then this bar is split. So while its mass is at certain radii, it's limited in the radii that the mass is located, because it only goes out to the length of the bar divided by 2. All right? you would probably have a question where you have to rank the moments of inertia. If you look back at the old test, you can see different configurations. Like sometimes it might just be a single bar, or maybe sometimes it's something more complicated like this, where it has two bars stuck together, or maybe like a square shape. Like for example, let's look at this shape. Let's say that I have a square, say a sheet of metal, and I have 4 points. We'll call it A, B, C, and D. Which of those points has the biggest moment of inertia? Then these are axes of rotation. So like this thing rotates around axis A, that means it rotates like this. If it rotates about axis B, that means it rotates like this, in the plane of the screen or the page. Which of these axes of rotation does it have the biggest moment of inertia? Is it A? Is it B? Is it C? Or is it D? So right now I'm asking what is the biggest, but then also in your mind ask yourself what is the smallest. But for your clicker, what is the biggest moment of inertia? The dots are axes of rotation. All right. So if it's rotating about point A, then this whole thing rotates around this point.
Okay, the square.
Right, the square. It's like a, well, you can think of it as your book, right? And so if this is point A, it rotates around that point. All right? Around which of those points does it have the biggest moment of inertia? A, B, C, or D? I'm going to stop at 120, or 125, we'll say. $125. Okay, awesome. A is right. A is at the very corner here. It has the biggest radii for all the masses, so you have more mass located at big radii, and that gives you a bigger moment of inertia. All right? Let's try the next one. Moment of inertia is which of these? Is it the rotational equivalent of mass, or you can read it? Which is it? All right, I'll stop at 25, or we'll go on to 30. 30. Five more seconds. Just guess if you're not sure. Awesome. A is right. It's the rotational equivalent of mass. So remember, as we're making these analogs, where we had M before, now we're going to have I. Say, you probably read this essay in your American Lit class, Civil Disobedience. You ever read that? You know what have you read it? You ever read Civil Disobedience?
Yes.
Some of you have. You know what makes that such a great essay? Thorough editing. It's written by, who is it written by? Thorough editing. Darlene. All right. Figure skater, have we done this one? We have not. Right. When she pulls in her arms, The first part of this problem is saying that L equals I omega. I is conserved, so when I goes down, when she pulls her arms in, omega goes up by the same amount. Now we're asking what happens to her kinetic energy. Remember, kinetic energy is 1/2 I omega squared. What happens to her kinetic energy? The first part is talking about momentum. If I goes down, when she pulls in her arms, she spins faster. All right, now what about her kinetic energy? What happens to her kinetic energy? Is it the same? Is it larger? Or is it smaller? All right, I'm going to stop at 130. 130. Okay, B is right. Now, it is true that her moment of inertia goes down, so that causes her kinetic energy to decrease, but her angular velocity goes up by the same amount. And since this is squared, then that means it's going to increase the kinetic energy. So let's say, for example, that the moment of inertia decreases by a half, and that would mean the angular speed would increase by a half. So how would that affect the kinetic energy? It would be how much bigger? Have a half times 2 squared. So the kinetic energy would be twice as big. Yes? Now, we said that energy is conserved, right? That you can't just have energy going around all the time. So where does this energy come from? If her energy increases, which it does, where does that energy come from? From the figure skater when she draws in her arms. Have you ever been on a merry-go-round that's spinning really fast? Right? Have you ever tried to walk towards the center? Have you? Are you serious?
I tried. I couldn't get
it. It ain't easy, right? Right. Like, it's not easy to walk towards the center if you're going fast, right? And so in a similar way, it's not easy for the figure skater to pull her arms in. So she has to apply a force over some distance. This on what? Work, right? She has to do work when she brings in her arms, and that's what caused her kinetic energy to increase. So she's actually doing work when she brings in her arms, which increases her kinetic energy. And the energy comes from her arms. All right, 2 different spinning disks have the same angular momentum, but disk 1 has more kinetic energy than disk 2. Which has the bigger moment of inertia? I'll get you started a little bit on this. We're saying that L1 is I1 omega 1, and L2 is I2 omega 2. They have the same momentum, but their kinetic energy is bigger, 1. All right, let's stop at 120, 120. Okay, B is right. You could have something similar to this on the test, but it wouldn't have the pictures. The picture sort of leads you into the right answer. The moment of inertia of this disk, which is bigger, is going to be bigger. But we can think about it too, that if L1 is equal to L2, all right, but I say that disk 1 has more kinetic energy, does that mean that the speed or the moment of inertia of disk 1 is bigger? We had this question earlier. They have the same momentum, but this one has more kinetic energy. So is the speed or the angular speed bigger for disk 1? What do y'all think? Now I know that their angular momentum and their speed have to add up equal. So like for example, if this is down by a factor of 2, then this has to be bigger by a factor of 2 than this. So they trade off in that way because they have the same angular momentum. So disk 1, which has more kinetic energy, is it going to have a bigger speed or a bigger moment of inertia? It's going to have a bigger speed because the speed is squared, and the speed being squared gives us an extra bump because they have that quadratic relationship. So the speed will be bigger for disk 1. That means that the moment of inertia for disk 1 will be smaller. So the speed is bigger, giving us more kinetic energy, because kinetic energy is more dependent upon the speed. That means that I1 is smaller. And so the one with the bigger moment of inertia is disk 2. And that's sort of what the picture leads you into thinking here. It's leading you correctly. Goodness bless you. All right, 2 buckets spin around in a horizontal circle on frictionless bearings, and suddenly it starts to rain. What happens when it starts to rain? We had a very similar question to this back in chapter 5. Remember we had the cart rolling on the tracks and it rained into the cart? Same idea here. All right, doing very well. We're going to stop at about 10 seconds at 55 seconds. 55. 5 more seconds. Guess if you're not sure. That's your neighbor. All right, awesome. A is right. Y'all remember the cart with the rain falling into it as it travels along? It slowed down. It slowed down, you remember, because of conservation of momentum. The mass goes up, so the speed goes down. The same thing is happening here. The mass in the buckets is increasing because water is falling into them, and so the bucket is going to slow down. Now make sure that the reasoning is correct, because the angular momentum of the system is conserved. And that is true, and that is the reason. The angular momentum remains the same, so if the moment of inertia goes up, the angular speed has to go down. It's good practice for the MCAT too, you pre-med folks, that often they'll have these questions that'll have not only the incorrect or correct answer, but also the reasoning as to why you put the answer. So just be aware of that. Oh, how did y'all do on that? Did y'all do well? Yeah. Did y'all know why the sand was wet? The seaweed. Okay. All right, let's move on to chapter 9. Are there any burning questions about chapter 8? You're going to see torque, you're going to see moment of inertia, you're going to see Newton's second law, you'll see conservation of momentum, and energy, rotational kinetic energy. Those are all the major topics. We'll come back, we'll have some review on this, but in the meantime, be doing the working through the old test questions, 20-30 minutes a day, work through the homework, work through the concept test. I'll post them online Friday, I think. I'll post them on Friday. Don't forget, there is an OpenStax quiz that's due on Friday as well. And guys, I'll probably have a quiz for this chapter 9 that we're on due on Tuesday. I'd like to get a couple more quizzes in. I know they're work for y'all, but it also is an exam grade, so it'll help you for those students that are a little bit more behind than they want to be. They want to have some extra quizzes. Okay? All right. Chapter 9's on fluids, solids and fluids. You've seen some of this stuff, I know, and some of it will actually be like from grade school, but some of it will be new to you as well. All right, so first of all, the states of matter, solids, liquids, gas. You can think of solids in the same sense of our rigid bodies, that you have 2 points in a solid, and they're always the same distance always the same distance apart. Remember, that's how we defined what a rigid body was. And in the same way, solids, the molecules or the atoms that make up a solid are set into place, and they don't move from that place very easily. Liquids, on the other hand, the molecules or atoms can sort of move around one another. They move around like a fluid. And gases, the molecules or atoms are separated far apart, and actually they rarely even touch. So solids have a rigid structure. Liquids have a more fluid structure in their atoms. And a gas, the atoms typically don't touch. They're very far apart. Collectively, liquids and gases are called fluids. A fluid is anything that flows, and so we'll call our liquids and gases fluids. Though usually when you're talking about fluids, you're talking about liquids, but fluids technically involve both liquids and gases. A plasma is a fourth type of matter. It is an ionized gas. With approximately equal numbers of positive and negative charges. So plasmas are often very hot. Like on the surface of the sun. On the surface of the sun or other very hot places, you basically rip apart all the atoms and you just got a big electron-proton soup. Everything's ionized. You have equal number of protons, equal number of electrons. But gases can also be ionized in other ways. Like y'all ever go into that really tacky store they have in the mall, Spencer's or whatever, they still have those things? Like where you can buy like the dog poop in a box. You know what I'm talking about? Yeah. It's not real dog poop, it's like fake. But they have those balls with that stuff. That's a plasma too. And you can create plasmas in other ways by having electric potentials. We'll see a plasma at the beginning of next semester with our big Van de Graaff generator. Okay, so you can make them in other ways. For example, if you have this ball, you get these little... You know what I'm talking about, right? You put your finger on it and it comes up to you. It's because of a difference in electrical energy, an electric potential. Oh, let's see. We're not going to show the clip from the Prestige. Dark matter. You could see a question about dark matter just asking you, what is dark matter? What is dark matter? We don't know. We don't really know what dark matter is. But dark matter is material that doesn't emit light. So matter that doesn't emit or reflect light. It was discovered, or it was inferred, sort of back in the 30s, and then again later in the 1970s, in a fairly interesting way. It was inferred through the observations of galaxies and their rotation curves, or rotation curves of galaxies. By Fritz Zwicky, and then later by Vera Rubin in the 70s. A rotation curve is this. If you have a galaxy that's rotating, it's rotating in this direction, and you can take a plot of the velocity and the radius. Pretty sure it's right. The velocity and the radius are starting out here. How fast are the stars going? And then the radius. And the rotation curve, shoot, I might get this wrong. And Caitlin, do y'all do rotation curves? And good. So I can just write whatever I want? Okay, good. So the speed should go down as you go out, and it should look something like that. The speed of these stars as they rotate, as they go about. But what they found basically is that the stars were going a lot faster than they should have been. So when they look at these galaxies back in the 30s and then again in the 70s, they saw that the stars were just going a lot faster than they should have been. And they compared if you look at how the stars are moving in a galaxy, then you can infer the amount of mass that's moving in the galaxy, because you know how gravity works and all that business, and you can calculate how fast the stars should be moving. And so you get a mass that we'll call the dynamical mass. The dynamical mass is based on these rotation curves. It says how fast are these stars moving, and then I can calculate what mass is in this galaxy. But then you can get a mass in a different way. You can look at the galaxy and just count the amount of light that's coming from the galaxy. And gosh, well, we call that I'll call it a light mass. I think it has a more technical term. You look at the amount of light that's coming from it, and then you can count, say, estimate the number of stars that's in the galaxy. And if everything is jiving as it should be, the dynamical mass should be equal to the light mass. Well, what do you think they found? If they inferred that a lot of the mass is dark, which of these would be bigger, the dynamical mass or the light mass? The dynamical mass. And that's what they found, that the dynamical mass is actually quite a bit bigger than the mass due to light in the galaxy. So that means that previously people had thought that most of the mass in galaxies was locked up in stars that put out light, and now they know that actually, gosh, I think it's something crazy, like 90% of the universe is thought to be made up of dark matter. People over the years have tried various things, ideas about what is dark matter. Like they've said that maybe it's rocks out in the solar systems, like in the planetary systems, or just in the galaxies, or maybe it's molecular hydrogen. Molecular hydrogen doesn't emit or reflect light very easily. And all those things just haven't really worked out. But it just hasn't been enough to account for 90% of the universe is dark matter. 90%, that's a lot of the universe. And so now we don't really know. It could be some sort of exotic matter, like not another state of matter, but a different type of matter that we don't really understand. But if you figure it out, Nobel Prize for you, and fame, lots of fame. Okay? So just know dark matter, it doesn't emit light, it doesn't reflect light, and that it was found by comparing these two different types of masses, and that the dynamical mass was bigger. All right, so let's look at the elastic properties of solids. If you go into engineering, I don't have any engineers in here, but if you do, you have whole courses that are based on this. But we'll just sort of go in short. We can define two things when we talk about elastic properties. Stress is the force per unit area. In fact, if you go into medical fields, you'll talk about the stress and strain as it relates to the human body, right? You stress a bone, what happens to it eventually? It breaks, right? That's stress. Stress is the force per unit area that you put on the bone, and then strain is the measure of the deformation of the solid. All right, so stress is the force that I put on it, and then strain is how it responds to that. So stress and strain are directly related, are directly proportional. So if I put stress on a material, that causes a strain. They are directly proportional. If I put twice the strain, or excuse me, if I put twice the stress, then I get twice the strain. This is a causal relationship. If I do stress, I cause strain. If I do stress, I cause strain. If you put too much stress, then you'll exceed the object's ability to change shape, and you'll break the bone or whatever, okay? The elastic modulus is a constant that's given, so the stress then, the elastic modulus just describes how the stress is related to the strain. The elastic modulus times the strain. We'll use this only in one dimension, but you can also find them in 2 and 3 dimensions. So let's look at that in terms of tensile stress and strain. If I have an object that's a length L naught, and I apply a force over a certain unit area to that object, that causes it to stretch. So you can think of, I don't know, a rubber band. If you apply a force per unit area to it, then I can make it stretch. F is the force. All this is in SI units, that's in newtons. L naught is the original length. Of course, that's in meters. A is the material's area. In this case, you know, this area, the cross-sectional area of the material. And then delta L is the strain of the material. It's the change in length. But that is our strain. I have this stress, it causes a strain. It causes a change in the length. Our equation that describes this is the stress, that's force over area, is equal to the modulus. This is Young's modulus. It's not me, it's some other Young from a long time ago. Young's modulus is just a constant, okay? So if I have a material, the way they determine Young's modulus is they apply a stress to it, and then they measure the strain. And when they do that, they can calculate what is that Young's modulus, and then the strain is delta L over L naught. Okay, this is on your equation sheet, but you'll probably have a question. We'll work through some as well, where I give you the stress, or maybe I give you the force in the area, maybe I give you the Young's modulus, or there's a table on your equation sheet that has Young's moduli for various materials, and then you have to figure out how much the strain is. This is the strain. Okay, we'll work through an example in just a bit. Here's some Young's moduli. As I said, these are on your equation sheet, I'm pretty sure. Am I right about that? Is it on the equation sheet? Okay, so let's try this quick test. I'll give you the Young's modulus there, though usually on a test I won't give you that. I'll just expect you to look on the table. be careful with your units here, okay? Everything needs to be in SI units. Now notice the options are all in centimeters. So you'll get your answer in meters, but then you'll need to convert it back to centimeters. All right, let's try to wrap this up soon. Somebody leave this flower for me.
Oh, that's me.
Did you seriously?
Well, she left it for Dr. T, but you can have it.
I'll take it.
Obviously get one.
I'll take care about you.
I thought it was poisonous, but I don't No, not like I left it for him because it was poisonous.
Oh.
I brought it. But it's not, so you can have it.
I'll take it back, Mom, and eat it.
Okay, cool.
I'll know if it's poisonous or not.
Yeah, they won't know. Die. Thanks, Maggie. Okay, let's stop at 355. So go ahead and guess if you're not sure. 355. Okay, I'm pretty sure B is right, but let me show you. So we say that our stress, that's F over A, is equal to our Young's modulus times delta L over L. And then, really with these, you have to pick out what is what here. So our force is 100 newtons. So I have 100 newtons. My area is 0.75 square centimeters. But remember, you have to have it in SI units. And I actually give you the conversion here. 7.5 times 10 to the minus 5 square meters. And then I need to know the Young's modulus. For a tendon, it's 2 times 10 to the 7th. That's in pascals. That's a Newton per square meter. We'll talk about that later. And then delta L over L. I don't know delta L, but I know the original length of it was 0.10 meters. And then if you solve for delta L, you get delta L is, was it B? Is it 0.007 meters? Was that what you got? Yeah. And so that's equal to 0.7 centimeters. Okay? There are some homework questions that are similar to this. You'll probably have one question like this on the test. All right, let's look at pressure, density and pressure. We had a lab on this. I'm pretty sure that you saw this in middle school or elementary school even, but you can see some questions as well. Look in the homework, look at some of the old tests, and we'll see some examples. Density, we're looking at volume density. Though, did you know that you can also have linear density and area density, where you have mass per unit length or mass per unit area? We won't deal with that. We'll only deal with the more typical volume density. Density is mass over volume, where m is the mass of the object. And v is its volume. And the SI unit of density is kilograms per mass per cubic meter. The density of water, just for example, is sort of good to know, is 1,000 grams per cubic centimeter. Or excuse me, not grams per, kilograms per cubic meter. Imagine that. If you have a cubic meter of water, that would be enough water to sort of fill this square right here, because these tiles are about a meter square. This would be 1,000 kilograms. Isn't that something? That's a lot of mass. Water's pretty heavy. 1,000 kilograms per cubic meter, and that's equal to 1 gram per cubic centimeter. Wow. Why is that? That the density of water is just 1. Like, is that some quirk of nature, you think? Have you ever thought about that? Like, why is the density of water an even 1? It's not like 1.00002 or whatever. It's 1. Isn't that amazing? Wow. Do you know why it's 1? No, Dad knows. Why is it 1? Huh? That's the standard, right? Remember we watched that Veritasium video way back in chapter 1 about standards of measurement? The standard for the kilogram is no longer the mass of water, but it used to be that a kilogram was based on the mass of water, of 1 liter of water. All right, here's some densities. This table is in your equation sheet. Notice that the density of ice is 917 kilograms per cubic meter. We'll get into Archimedes' principle, but you probably know, what does that say about ice? That the density of ice is less than the density of water. That ice does what? It floats. In fact, it's kind of unique in that way, that most liquids, when they become solids, they get a density that's more than the liquid. And an object that has a solid that has a density that's more than its liquid will do what? It won't float, it'll sink if it has a density that's more. So have you ever thought about what would happen if water was that way? That if when it solidified, that the density actually increased? What would happen? Well, we would live on an ice planet, right? Because whenever water would freeze, it would go to the bottom, and then more ice would freeze, and it would go to the bottom, and then more ice, and we'd probably be dead. We probably wouldn't even be here. But isn't that remarkable that water, which we depend upon to drink and bathe and stuff like that, that it has that unique quality that most materials do not. All right, and specific gravity, we're not going to see specific gravity. I'm not going to use specific gravity, but it just compares the density of the substance to the density of water. You probably had that in chemistry class. You could see it on things like the MCAT or the GRE, specific gravity. So for example, the density of aluminum, which is 2,700, specific gravity is 2,700 divided by the density of water, or 2.7. But you're not going to see it in this class. Let's try this clicker question. I'm going to go away for just a second. I'll come right back. All right, I'm going to stop at 42. Just guess if you're not sure, though. I think everybody has it right. Oh. It's okay. You got it wrong. The answer is A, that the block, or not A, B, that it's less dense than a fluid, and so it floats. We know that's sort of intuitive, and we'll get into it in Archimedes' principle, which describes this buoyant force. And some of you have seen that in lab already. Let's see. Did you hear about the butcher that backed into his meat grinder? You hear about that guy? He got a little behind in his work. That's like the best one also. All right. All right, let's look at pressure. Oh, y'all thought you were going, didn't you? So, pressure. I'm going to use a capital P. And my P's, I always put a little base on them to tell them apart from rho. Get over it. That's how I write my P's. Maybe one day you'll start writing your P's that way too. So, P is equal to force over area. Force over area. The SI unit for pressure is the Pascal. He was a mathematician, philosopher, theologian, Pascal. And 1 Pascal is equal to 1 Newton per square meter. So our basic SI units are in newtons per square meter, but we use pascals. We'll also use the unit of atmospheres, and 1 atmosphere is equal to 1 times 10 to the 5th pascals. Let's see, I'll show this little video and then we'll wrap it up, okay?